Good morning, class, and welcome to this lesson on Magnetism 13, Lenz's Law. Today, we will be able to determine the direction of current for a changing magnetic field. We will be able to determine the direction of current for a changing magnetic field. So this is Lenz's Law, verbatim. Lenz's Law. The induced EMF resulting from a changing magnetic flux has a polarity that leads to an induced current whose direction is such that the induced magnetic field opposes the original flux change. Now, I know many of you read that and you probably have this down packed, but for those of you who don't, let me go ahead and explain this because I know that definition is very easy to understand. So, let's go back to our objective. With this law, we are going to be able to determine the direction of current for a changing magnetic field. That's what this is saying. If the magnetic field is changing, we will be able to determine the direction of current, okay? Because the direction of current is going to oppose the flux change. The direction of current is going to oppose the flux change. So let's take a look at this. Let's recap for a second here. We know that if we change the flux through a surface, and in this example right here, we are changing the flux. The flux is increasing from this side to this side. There is more magnetic field lines going through this area than this one. So when we change the flux, we induce a current. It literally is called an induced current, okay? We have an induced current due to a change in flux. Well, we know when there is a current has a direction. A current creates its own magnetic field. A current creates its own magnetic field. So, what's going to be the direction of this current when we change the flux? And that's what Lenz's law is saying, okay? So, let's do an example and get this law down. Here we have an example of a conductor, a metal ring, that enters a magnetic field, goes to the magnetic field, and leaves the magnetic field. So the basic question here is, what is the current? What is the current at positions 1, 2, 3, 4, and 5? Well, positions 1 and 5 are very simple. There is no magnetic field going through these rings. So the current through 1 and 5 is 0, okay? So 1 and 5 is equal to 0 amps, okay? Somewhat easy, but not as obvious. Position 3 has 0 amps because at position 3 there is no flux change. At position 3 the flux is constant, and because the flux is constant, there is no flux change, there is no current. So position 1, 3, and 5 are pretty simple, but really Lenz's law applies to situations like 2 and 4. So at position 2 the flux is increasing. The flux is increasing. So if we go back to our definition, an induced current whose direction is such that the induced magnetic field opposes the original flux change. It's going to oppose the original flux change. So, because the flux is increasing, the magnetic field due to this ring, because this ring will produce its own magnetic field, and because this magnetic field is going into the page, the magnetic field due to this ring is either going to be into the page or out of the page. It's going to be one or the other. It's going to be into the page or out of the page. So, because it is increasing, the flux change is going to be opposite what's going on. So the original flux is going to be opposite the induced flux. Okay, so the original flux in this situation is going into the page. That means the induced flux due to position 2 is going to be out of the page because it's going to try to keep it the same. And so if we did our right hand rule right here, if we did our right hand rule on this ring, our thumb would end up curling around this ring counterclockwise, so our fingers would curl under it and point out of the page. Our fingers would point out of the page. So the current at position 2 is counterclockwise. The current at position 2 is counterclockwise. So this is position 2. This is position 2. I'm sorry, I didn't write that earlier. Let's go to position 4. Let's go to position 4, okay? Now the flux is decreasing. Now the flux is decreasing. Okay? We have our original flux. I put our original magnetic field. Our original magnetic field. Okay? And we have our induced field. Okay. So, because we are decreasing field lines here, because we are losing the amount of field lines going through this circle, our original field lines are going into the page. This means our induced field lines are going to go into the page as well. So they're going to be the same direction. So let me go over this one more time because I feel like I probably just lost some of you. In this example up here, let me erase this. In this example up here, as the ring was entering the magnetic field, we were adding, I'll write this down. We were adding field lines. We were adding field lines. We were increasing the magnetic flux. The current wants to oppose that. If we're adding, the current wants to make it subtract. If we're adding, the current makes it want to subtract. So therefore, the current, the magnetic field, due to the current, due to the induced current, had to be opposite. Because we were adding field lines, we had to subtract. If the field lines were going into the page, due to this current, it wanted to come out of the page. Okay? Down here, we are subtracting field lines. We are subtracting field lines. Because we are subtracting field lines, because we are making them less field, we are making less of a magnetic field, the induced current wants to add. The induced current wants to add. So before, the original and the induced, the original magnetic field and the induced were opposite because when we added, we wanted to subtract. So they're opposite. Now that we are subtracting field lines, the induced current wants to add. So it's going to add on to the original. So if the original is going into the page, then the induced current is going to go into the page as well. So that means that the current in this situation, if we take our thumb, if we take our fingers and go into the board, our thumb will curl around in the clockwise direction. So the current here is clockwise. Okay? The current there is clockwise. So, if what I just said doesn't make sense, well, I understand it's probably going to make sense at first. It takes a little while to get this concept. This chart I gave you is what you need to understand. If the magnetic flux is increasing, the induced current is going to be opposite the the induced field is going to be opposite the original field. In this case, the original field's into the page. And if we are decreasing flux, the induced current will be the same as the original current, because when we add, the induced current wanted to subtract. And when we subtracted, the induced current wanted to add on to the original.